Hello, we are Group 4. Our project is to design a low-cost ventilator for developing countries. My name is Sarah Abdo, and I'm an electrical engineering major.
Hi, my name is Melissa Keefe, and I'm a mechanical engineering major.
My name is Olivia Kelsey, and I'm also a mechanical engineering major.
My name is Migliaccio, and I'm a mechanical engineering major.
My name is Nataniell Ilyayev, and I'm also a mechanical engineering major. When we began our project, we started brainstorming on how we can make the project as efficient and as beneficial as possible. This resulted in us in focusing around a low-cost approach in regards to materials, production, and assembly. We utilized 3D printing for all of our parts and components that we could. Our main compressor system uses AmbuBag instead of a medical-grade air compressor. This dramatically reduces the price and packaging of the ventilator. Our volume-controlled feedback system is Arduino-based and interfaces with MATLAB to output our flow data. And the modular arm design allows for multiple bag uses, meaning child, infant, or adult bag sizes.
In the recent COVID-19 outbreak, a demand for ventilators was highlighted for patients suffering from respiratory illnesses. This increase in demand brought different relating issues into light, including a more versatile ventilator option and a less expensive ventilator option. In order to address this problem, the prototype utilizes low-cost alternative methods in designing a compression mechanism.
When designing a mechanical ventilation system like ours, different human constraints need to be considered. These human constraints are dependent on the size and condition of the user's lungs. These two parameters include the tidal volume and the compliance of the lungs, of which the governing equations can be found below.
The main mechanical feature of the ventilator is the compression cycle. It consists of a frame that holds the bag together, an I-beam that holds the compression arm, and the compression arm that's attached to a pulley system that's attached to the motor. This is reduced to a 4-bar linkage, and the arm compresses 65 degrees from its resting position to its fully compressed position. This displacement is used to analyze the flow rate and the desired flow rate and tidal volume for the patient's needs, which is set by the doctor's breaths per minute. The sensor is also mounted directly to the AmbuBag. This is a direct fit sensor, therefore it's easy to use and is very interchangeable.
We simplified the mechanical design into a 4-bar system. The picture on the left is the assembly of the mechanical components in SolidWorks, and on the right is the simplified 4-bar system. As you can see in the video clip, our 4 represents the motion of the band and the pulley attached to the motor, and it's going to decrease and increase in length, and the angle will change as well.
Regarding electronic features, a Sensorian volumetric airflow sensor is implemented to measure continuous airflow and monitor the patient's breathing cycles. The digital I2C sensor is compatible with the Arduino microcontroller, making it possible to read the data from the sensor and code a graphical user interface so the user can make appropriate observations from the outputted volume versus time graph. To be able to make any circuitry connection with the sensor, wires were carefully soldered to the PCB board of the sensor. As can be seen in the figure, this is the circuit schematic containing both the sensor and Arduino.
So as we designed our prototype system, we tested different compression arm shapes. The first iteration was a flat beam that did not compress the AmbuBag uniformly, and the second had the same curvature of the bag, but did not compress the bag the desired amount. And for the final iteration, we inverted the curvature beam, and this model was able to uniformly compress the bag to our desired depth. And originally, we decided that we would use a stepper motor for the compression of the AmbuBag, since stepper motors are good for precise movements when the load is constant and disturbances are limited. However, the patient's airway resistance and lung compliance can change over time, and a geared DC motor with an encoder was substituted to deal with these dynamic load changes.
The volume-controlled ventilation system runs on this volumetric flow rate sensor. It's calibrated using the flow equation provided by the manufacturer in standard liters per minute. Calibrating it consists of setting a set flow rate through the sensor and measuring the output voltage provided by the sensor. This is then calibrated into the MATLAB GUI, which interfaces with the Arduino motor control.
Looking on to next semester, our key milestones are going to be reevaluating the prototype from SUNY Design 1 and implementing any suggestions, consolidating the housing design, looking into the sensor interface and the GUI, also looking into an oxygen system, and then coming up with a final prototype and spec sheet.
As mentioned previously, we selected a DC motor, and some of the key specifications of this DC motor is the gear ratio of 188:1 and the stall torque of 33 foot-pounds and the 5-volt DC encoder. Another important feature of this DC motor is that it can be back-driven. This is important in the event that there is a failure in the system and manual pumping of the bag can occur until the issue is resolved.
Using different inputs from the motor, a targeted speed of 2 seconds per compression, and ease code was comprised to find an ideal circumference of the pulley. From there, this ease code can then further be developed in next semester to add any other needed remediations to the implementation of the motor to our design.
So we also looked in the gear ratios because we needed to increase the speed of the motor output, the output from the motor. So this shows a 10 to 15 gear ratio design, and it increases the speed of the motor from 28 RPM to 42 RPM.
Regarding sensor interfacing, using a code on MATLAB, we are able to create the GUI to output a volume versus time graph for the user to make the appropriate observations. The image on the left presents the control system of the design. Between the dashed lines are what we have accomplished this semester. It can also be seen that the volumetric flow sensor is connected to the input pins in the Arduino, which will allow MATLAB to read the data received from the sensor. The image on the right presents an example of what the volume versus time graph from a ventilator system that would appear on the GUI. Looking at the control system design, when implementing the motor in the designs, signal conditioning must occur to consider the amount of current needed to drive the motor. There will be a current amplifier added to the design to ensure the motor receives the power required to pressurize the airbag.
We also just want to give a special thanks to our 2 advisors and the professors for helping us through our first semester senior design.